Go.
Alright. Part A says determine the electromagnetic force of this battery right here. Electromagnetic force meaning the potential difference voltage. So we have E is also voltage. We know the equation V equals I R. So we have that this one, we have to find the electromagnetic force of the battery right now. So we can find it when at time equals 0 seconds. So I not R. This turns out to be electromagnetic force is equal to 10 microamperes times 2 times 10 to the, what is that, 6 ohms. Microamperes being micro, so this is the same as 10 times 10 to the negative 6 amps. And these cancel out, giving us electromagnetic force of 20 volts. Okay, part B. By evaluating an appropriate integral, develop an expression for the charge on the right-hand plate of the capacitor as a function of time for when time is greater than 0. It's going to be B. Alright. So we have to develop an or appropriate integral developing an expression for the charge. So we can use this equation. I equals, or the current is equal to dq over dq that dt. And when you move it around, you can get that equation to be q is equal to the integral of I dt. I will be a constant. Let's treat it as a constant for now and move it to the side. So now we get q is equal to I naught integral, and we have dt. So that's for that we're going to use this equation right here, because I is equal, or I dt is equal to that. Remember this right here. I dt is equal to this. So we have the integral of I naught, which I moved over here to the side, down marker, e to the negative t over 6. And when we anti-derive that, we get q is equal to I naught negative 6 e to the negative t over 6 plus c. I'm going to move this over here. And we know that q, or the charge on the plate, is equal to 0 when t is equal to 0, because the switch has not been closed. So we can get that 0 is equal to, how to move this? I can't believe I forgot this part. Right. I naught negative 6 e to the negative 2 over 6. Let's see.
When your battery?
Yeah.
Oh shit.
Oh yeah. Alright, my bad. Okay. We got 0 when time is equal to 0. So we got I-O negative 6 e to the 0 divided by 6 is the same as e to the 0, which is 1. So we got negative 6 I-O times negative 6 plus c. So we move this over here to the other side, and we got 6 I naught is equal to c. So that's the charge in the right-hand capacitor. That's B. Just put C. C, it says on the axis below, sketch a graph of the charge on Q, the capacitor, as a function of time. Yeah. Alright, so this asymptote is going to be the maximum charge the capacitor will be able to hold. And we all know, as time goes onwards to infinity, the Q will reach that maximum point, or will always be slightly lower than the maximum point. And it reaches it exponentially, so the graph should look like this. Part D. Determine the capacitance of C. A. So we got C equals Q over V. We know V is equal to IR. So you can change this to C equals Q divided by I R. And we can move the R around and make this C equals 1 over R times Q over I. And we found previously Q, well, this will end up being C equals 1 over 2 times 10 to the 6 times 6 I naught e to the negative t over 6 divided by I naught e to the negative t over 6. These cancel out, leaving us with c equals 6 divided by 2 times 10 to the 6, making this equal to what is it? 3 times 10 to the negative 6 micro, or not micro, but farads. That's it.
What? Is that it?
Yeah.